Why don't wind turbines spin faster and faster as the wind gets stronger? If the wind is free power, what's stopping the rotor from turning into a giant runaway propeller? Because a turbine isn't trying to spin fast. It's trying to stay in a safe, efficient sweet spot. Like riding a bike downhill. If you never touch the brakes, the wheel's speed climbs until something fails. A wind turbine constantly touches the brakes, but mostly using aerodynamics, by twisting the blades, so speed stays controlled while power stays useful. First, let's kill a common myth. More RPM means more power. For wind turbines, that's backwards. Power comes from torque times rotational speed, but torque isn't guaranteed. As RPM rises, the blades don't automatically keep grabbing more wind. In fact, if they spin too fast for the wind speed, they start slicing through air that can't refill the space fast enough, like trying to scoop water with a bucket you whip around too quickly. You move fast, but you catch less. Engineers describe this with a simple idea. The rotor wants to run at a specific tip speed ratio, how fast the blade tips move compared to the wind. In that zone, the blades make strong lift and steady torque. Outside it, efficiency drops, loads spike, and the machine gets noisy and stressed. So turbines use two big control tools: generator torque control and blade pitch control. When the rotor turns, it drives a generator. A generator doesn't just produce electricity, it also pushes back with resistance. That resistance is torque. More electrical load means more opposing torque, which slows the rotor down. In older systems, you might think of it like hooking the generator to more stuff and feeling it get harder to turn. Modern turbines do this with power electronics. They decide, moment by moment, how much torque the generator should apply so the rotor speed stays where it should be. At moderate winds, the turbine often runs in a mode that lets RPM increase a bit with wind speed, because staying near that sweet tip speed ratio keeps the blades efficient. As wind rises, the controller increases generator torque to harvest more power without letting the speed drift into dangerous territory. But there's a ceiling. Past a certain point, you don't want more power, you want less stress. This is the part most people miss. The blades are not fixed paddles. They're wings, and each blade can rotate around its long axis. That twist is called pitch. If you pitch the blade to the best angle, it makes strong lift, big torque, great power. If you pitch it away from that angle, lift drops, torque drops, and the rotor stops trying to accelerate. So when wind gets too strong, turbines don't fight harder to capture everything. They do the opposite. They spill wind on purpose. They pitch the blades toward a feathered position so the wind slides past with less force. This is aerodynamic braking, and it's elegant. You reduce torque at the source before it becomes mechanical violence inside the drivetrain. Here's a quick mental image: a desk fan with blades you could twist. Twist them to a steep angle and the fan bites air hard. Twist them flatter and it freewheels. Turbine blades do that continuously, hundreds of tiny adjustments, so rotor speed stays calm. Because the turbine has limits that don't care about your optimism. Tip speed and noise. Faster tips mean louder aerodynamic noise and more turbulence. Centrifugal loads. Doubling RPM doesn't double stress. It can make loads explode. Fatigue. Gusts create repeated bending cycles. Higher speed can mean more damaging oscillations. Resonance. Every structure has natural frequencies. Overspeed can wander into dangerous vibrations. Grid limits. The electrical system has constraints too. Sometimes you must cap power to protect equipment. So turbines have an operating plan. Below rated wind. Chase efficiency, increase power smoothly. Around rated wind. Hit the target power and hold it. Above rated wind. Pitch blades to shed energy and protect the machine. Extreme wind. Stop entirely. Yes, turbines have mechanical brakes, but they're not the main speed controller. Mechanical brakes are mostly for parking, maintenance, and emergencies, because clamping a spinning rotor with huge energy can cause heat and wear fast. The usual shutdown sequence is pitch the blades to reduce torque first, let the rotor slow, then apply the mechanical brake near low speed. Many turbines also have redundant overspeed protection. If pitch control fails, backup systems pitch or stall the blades, and the brake can engage as a last resort. Because there's a difference between powerful wind and safe wind. Turbines have a cutout wind speed, a point where continuing operation risks damage more than it earns energy. When storms bring chaotic gusts, the safest move is to feather the blades and lock the rotor down until conditions return to normal. So the turbine isn't being lazy, it's being engineered. The goal is not maximum RPM. The goal is maximum lifetime energy without catastrophic failure. Now you know the trick. Turbines don't run away because engineers control torque with the generator and control the wind itself with blade pitch, and brakes are the backup plan. Next question. Why do some turbines have gearboxes while others are direct drive?